And Harrison for having me up. It is fun to come to DC, get into the big city, leave sort of the brick-filled college town that I live in. And I want to take the next little bit to give you some insight about Oman's geology. And one of the things about this I realized in putting this talk together is that Oman's geologic heritage, if you will, is so rich, so deep, so wonderful that I couldn't pack it all into the time I have. So hopefully at the end, if there are questions about all the things that I don't talk about, we can get into those. But what I want to do is give you a sense about why I study in Oman, and one of the things that makes it one of the most distinctive sort of geologic locations on the planet. So, to give you a background before we get into this, I've been fortunate to run for the last few years a Waymarried program to Oman, and I partner with Anne Rasmussen, who you can see in the lower left-hand corner here. Many of you may know Anne. She's an ethnomusicologist. And Anne and I put together this course that is colloquially, informally known as Rock Music Oman. Its proper title is Natural History and Contemporary Culture of Oman. We ran it for the first time in 2016, and you can see sort of that group in the photo here. And it's really been a fabulous opportunity for us to do the things that we like in a spectacular setting. So sort of by day, we are seeing the landscape, and by evening, we are sort of soaking up the contemporary culture of Oman. So we're going back this year. We have 24 students that are signed up for the 2019 program in January. And we're excited, but we have a little trepidation thinking about how many will be sort of forging across the deserts there. But I have an interest in Oman because I am a structural geologist. And if you wanted to sort of crisply and cleanly characterize what a structural geologist does, they're basically a scientist who's interested in the architecture of the Earth's crust. How is the interior put together? How does it change over time? And how does that actually impact what we see at the Earth's surface? So in the image here, which is a fabulous road cut, the big highway between Muscat and Nizwa, I hope you can see that there are a sequence of these geologic layers, these strata here, and they are tilted. Originally they would have been deposited or laid down in a nearly horizontal orientation, but now they're sort of cantilevered to probably 60 degrees from the horizontal. And this is really the bread and butter of what I study. How did they get that way? When did that actually happen? And Oman is a spectacular location to actually go see these rocks and structures that have formed during Earth history. So those are tilted strata, sort of just around the corner, literally, in a wadi not far away. If you look closely, I hope you can see, and it'll help when I hit the animation here, the actually strata here have been folded. They've been contorted into a series of layers. These are anticlines or synclines. So for me, I would like to know, when were these layers of sediment squeezed and buckled, like you can see here. And we can sort of continue with this progression from tilted layers to buckled layers to layers that are contorted almost beyond belief. This is a photograph. This is actually a gigapan image constructed from many, many overlapping photographs that I took on a cliff face near the capital. And if you look in the distance here, hopefully you can see the layers, right? But it's always helpful if you annotate an image. And so trace the pink layers now. And these are some of the most crazy folds on Earth. In fact, these are known as mega sheath folds. The shape of these layers, they've been almost wrapped around themselves. They've been drawn out into these long cylindrical structures. And to give you a sense of scale, hopefully you can see that they're bushes. They look pretty tiny, don't they? Power lines there. So this is a cliff face that's on the order of 1,000 feet high. And this is the world's best example of a sheath fold, right there for us to see in a wadi in northern Oman. But we really study the process by which how these rocks actually get that way. And our thoughts on this come from the idea that we take original layers of rock and we shear them with great intensity under the right conditions, and we can take original sort of irregularities and we can draw them out, if you will, into these sort of eye-shaped folds. Really extraordinary to think about the solid earth being transformed over time into structures like that. So that was part of what drew me to Oman. And part of what I've tried to do in the 5 or 6 years that I've been studying Oman is write in a very public, outward-facing way about the geology of Oman. So in most of my talks everywhere, I pitch my blog. And I do that because I can't even get my mother to read my blog. So I figure I might as well reach out to anyone I can. But the whole idea here is that the geology in Oman is spectacular. Not necessarily many Americans know about it. And one of the things I would like to do is, as time rolls forward, have more and more Americans that are actually there doing what you might argue is geotourism, from that all the way to what I would say is proper sort of geologic research. So you can check out Chuck Bailey on the We Marry blogs. Okay, let's set Oman up sort of in the world and the region. Oman is a country at the eastern edge of Arabia. I've outlined it here. It's got a long, long coastline. And so, you know, as a country, Oman has certainly been the edge of the Arab world, facing out towards the Indian Ocean and regions beyond that. But let's put a little geology onto this image. And here I've sort of faded back the terrain, but hopefully you get a sense of some of the geology here. Oman is on the Arabian tectonic plate, and it is sort of its own microplate that is separate and distinct from Eurasia, which is to the north, and Arabia, which is, Africa, which would sit to the southwest, and then further to the east, the Indian plate. And we're probably all well aware of the fact that India is colliding with Eurasia, and it's throwing up the grandest mountain range on the planet right now, the Himalayas. But there are a set of actually actively forming mountains all around this region. The Earth's crust, Arabia, is actually being subducted under southeastern Iran. And then as you go further north into the Arabian Gulf, the Arabian plate is actually crushing a series of mountains known as the Zagros across that region. And this is in part happening because at the very same time we are opening up a new ocean along the Red Sea. I'm trying to sort of stay suitably behind the lectern here, but I'm going to slip over very quickly. These are zones of rifting where we're opening up new crust, and we've created, really in the last 20 million years, geologically speaking, that's not so long, things like the Gulf of Aden and the Red Sea. So it's an interesting region. Oman itself is not directly on any of these boundaries. So what we see in Oman is primarily ancient deformation. But what it tells us is really significant about sort of Earth history and Earth evolution. So, oftentimes I want to give a scale comparison. I think, at least for many Americans, it's hard to get a sense of, well, how big is Oman? So what I've done here is I've just sort of outlined Oman and put it against the mid-Atlantic region. And you know, they're broadly of comparable size and shape. Most of my work has been in the north of Oman, and that's what we're going to stick to today. Even though the south of Oman is a spectacular place in its own right, the Dhofar region and the mountains near Salalah. But today we're going to focus really on the North Oman Mountains, the Hajar, if you will. And one of the things that probably would come out better if I hadn't put text all over this slide is the North Oman Mountains are very distinctive. Color-wise, they are a region that you can see in satellite image, and they're sort of this dark, ruddy brown. And that's in contrast to the sort of gravelly deserts that you have to the south, or the sandy deserts of the Empty Quarter, down here in the corner with Saudi Arabia and extending further south into Oman, or the Sharqiya sands, which are right about here. So these are high, rugged, dark mountains, and the rocks in them really tell this story about the deep earth. So here's a more zoomed in view of the North Oman Mountains, and I'm going to show variations of this map along the way. And this is a type of map that Earth scientists call a shaded relief map. So I've color-coded it based on the elevation of the land surface. So if you're at sea level, it's blue, and it goes up from there. In fact, if you get over 2,500 meters, you end up in these white colors here. So this is kind of the region between Muscat, Nizwa, Sohar, and Ibri. And this is a really good patch of ground if you want to see sort of geology. It's rugged, and the two sort of parts to this are important are Jebel Akhtar, sort of the great green mountain, which is this fabulous range, and then the Batna coastal plain. If you've ever been to this part of Oman, or you've driven the now big fast highway from Sohar to Muscat, you're traversing this coastal plain. It's much like the Atlantic coastal plain here in the mid-Atlantic, sort of gently sloping towards the ocean. Obviously, they have date palms there, and we don't have those in the mid-Atlantic, but similar in its sort of physical geography. Jebel Akhtar is a spectacular mountain range. It's actually got the highest peak in Oman, Jebel Shams, which is over 3,000 meters and is a pretty impressive piece of terrain. as we'll see, I think, in a little bit here. So let's zoom in a little more closely to this area. We're going to zoom in right here into this box. And in this box, we'll pull up the Google Earth satellite imagery. And you can see the gravelly plains to the north of the mountain ranges, Jebel Akhdar in the south there. And then I hope your eye is sort of drawn to the stuff that's in the center here between Mantle and Rustak. These are really rugged brown hills, very distinctive terrain in this satellite view. So again, what I'm interested in having you look at is this area here. Very brown, it's very rugged, and it's got a texture that's extraordinarily different than the gravel plains and then the high mountains of the Jebel Akhdar. So we're going to zoom in one more time, getting a little closer. And almost at every scale you look, this is a rugged landscape. This is a scene near Subakaya, and the wadi, it makes a sort of a distinctive track cutting through it. But this is an intriguing landscape. I mean, even from space you can see that. And I remember as a geology student learning about this terrain and thinking, you know, I need to go there. And this terrain is in some ways like very few others on Earth. And this is the terrain that it makes up part of the Oman ophiolite. Sometimes it is referred to as the Samael ophiolite. I'll probably use those terms interchangeably. But ophiolite, if you learn one thing today, I hope you learn a little bit about the ophiolite. My wife sometimes says, Chuck, you like the ophiolite so much you should have married the ophiolite. But the ophiolite offers this window into the deep earth that we don't see in most places on the planet. So an ophiolite is effectively a slab or a piece of ocean crust and the mantle that occurs below it. And what makes it unusual is that this ocean crust and mantle somehow was emplaced onto the continents. It's originally derived, it's a compound word from sort of the Greek, ophio for snake, and light or lithos for stone. These were first sort of coined, this name was coined in the Swiss Alps back in the early part of the 19th century, if you will, and then it's sort of been resurrected a number of times. And in early 1970s, there was a conference to come up with what really is an ophiolite, so now we have a nice codified name. It's not one rock, it's actually a variety of rocks. And originally it got its name because many of the rocks in these ophiolites are scaly, and the idea is that brought up some connotation that this sort of a rock that looked a little bit like snakeskin. So I'm going to hand out some samples of ophiolite here, but again, it's multiple rocks, and they tell the story of what was happening on the ocean crust and into the deep mantle. The image on the right is that's to the right, is actually a simplified model of what the structure of an ophiolite would be from the very top, which really represents what would have been the ancient seafloor, all the way to the mantle, which would have been the deeper material below it. And we're going to work our way through that complex, because if you want to see ophiolite, Oman is the place to go. Here is actually a map of worldwide ophiolite belts. And I've starred the Oman ophiolite. Ophiolites aren't rare, but they're not common. They occur in mountain belts around the world. But the trouble with this map is it makes them all look equally good. And they're really sort of, if you were going to give Olympic medals for ophiolites, the Oman ophiolite would take the gold medal. The ophiolite exposed in Cyprus, the Troodos ophiolite, would probably be the silver medal. And then the New Caledonian one, which is out here in the Pacific, would be our bronze medal winner. The rest of these are there, but they're much smaller, they're harder to see, all those kinds of things. So part of why I've gone to Oman to study is to better understand the ophiolite. And it is a massive, massive part of the North Oman Mountains. Everything here in green is part of the ophiolite. It lengthwise extends from really UAE to the north of this image, just to the east, southeast of this image, about 600 to 700 kilometers in length. It occupies an area about the size of the state of South Carolina, and there's no other ophiolite in the world that comes even half that size. And in Oman's climate, it is extraordinarily well exposed, so the access to it is amazing. So we're going to look at a few locations in North Oman, trying to sort of think about the ophiolite. The outlying regions, Buwa and Wadi Hawasana, are two of our study areas that I will probably come back to a little bit later in the talk. But again, the ophiolite in this image, they're the green materials that are there, and they have sort of an interesting relationship with the other colors on the map, and we'll see that as we move along here. So, let's take a trip to a big wadi west of Sohar, Wadi Jazid. And this is probably the most spectacular exposure in the world of pillow lavas. And here is a photo of an outcrop of ancient lava that was erupted effectively on the seafloor. So modeling in front of this is Alex Johnson, one of my former research students. He's working on his PhD at the University of Santa Barbara right now. So he was the first research student I took to Oman. We sort of cruised around together for 2.5 weeks seeing the sites. But the scale of this outcrop is tremendous. If we zoom in a little more, here is Alex in a slightly different light. But you see all these curiously shaped entities there? Those are what geologists know as pillow lavas. And pillow lavas form by volcanoes erupting on the seafloor. We observe them in the next picture. We'll sort of show you modern ones forming today under 3 kilometers of water. The other thing you can see in this image are a series of cracks or dikes that were filled with further lava that would have happened after these erupted. The seafloor cracks and you inject more into it. So fabulous exposures of this stuff. So here is a basically submersible image of pillow lavas that are probably a few weeks old that formed in the mid-Pacific. And that process happened 90 million years ago in what is today Oman. All right, I thought this was a pretty clever shot. Here are my research students napping on the pillow lavas at Wadi Jazid. So this is a spot that has drawn sort of geologists to that corner of Oman really for 30 years, and pretty spectacular. And that's part of the reason that Oman should be rightly proud of its sort of geologic heritage. And then I think the other component of that is to think going forward how it protects its geologic heritage. As I said, this is probably the best exposure of pillow lavas on the whole planet. Below the pillow lavas, there are a set of cracks that are known as sheeted dikes. If you fuzz your eyes up a little bit, maybe in this scene, you can see some of these vertical features in the rock. And those vertical features are actually dikes that would have fed those pillow lavas. So I realize I have a table of rock here, and I need to pass these rocks out. All right, so we're going to try this, see how it works. This is actually an Aloni Basalt, all right? So these are the rocks that were erupted as pillow lavas. All right, and what we've actually done is sawed it, so this is not a natural face, but this is a little chunk of Omani rock that once was lava on the seafloor. But if you continued down through this tour of the ophiolite, you would end up in a series of igneous rocks known as gabbro. And these gabbros are layered, and that layering happens as you inject magma and some crystals settle, other materials actually float. And so over time, you build up these layered igneous rocks. So here is a bit of the layered gabbro, all right? And at the very least, they'll say, oh yeah, it's layered. So part of the reason scientists have sort of flocked to the Oman ophiolite is this is the one place in the world where we can kind of see the ocean crust from top to bottom. And we can learn about the processes that make ocean crust on our planet. And that's really a fundamental way we create continental crust. And the idea is that this large turnip-shaped thing is a magma chamber where we are extracting magma from deep in the earth. It rises up, and there it segregates and separates. Some of it will cool, but some of it will actually get ejected higher up into a series of cracks and then make these pillow lavas on the seafloor. And in North Oman, you can literally walk through this sequence because these rocks are exposed and turned on their side. Okay? But the other thing that makes the ophiolite special is that much of it is actually rock that we think originates originally in the Earth's mantle. And the mantle is the layer underneath the Earth's crust. And these are dark, dense rocks. They're low in silica, they're high in magnesium, they're high in iron. And when it comes around, I hope you'll sort of feel the heft in this little tiny hand sample. So these are the rocks that we rarely, if ever, see at the Earth's surface. And Oman is a perfect sort of outdoor laboratory, if you will, to go examine these things. Now, we're going to take a little trip here, and as I mentioned a moment ago, the great thing about the Oman ophiolite is it's turned on its side, and as you go across the landscape, you can effectively go from top to bottom of that sequence. And where we're going to go is to an exposure between these crustal rocks and mantle rocks. And that boundary is something known fondly by most geologists as the Moho. I mean, at the very least, it's fun to say, all right? We're going to go visit the Moho. And in cross-section, you might think about it this way. This pink boundary right here actually separates what was once ocean crust from mantle materials. And this is what it looks like when you walk up to it, all right? There's some Omani lads that are having a nice day in the wadi swimming. But that fundamental boundary on planet Earth is exposed right here near Subakaya. It's exposed in literally dozens and dozens of places around Oman. So for a geologist, this is truly going to a place that is very special because the Moho, this boundary between the crust and the mantle, is probably 35 kilometers below our feet here in Washington, D.C. So it's not really accessible to direct observation, all right? Now, to do right by things, I need to give you a little bit of a description of how the Moho got its name. It turns out, if we go back to 1909, there was a Croatian seismologist who recognized that seismic waves sped up the deeper they went. And the images sort of in the background there kind of illustrate it schematically. And what he was able to do was say this must be a boundary between two units or layers of the Earth where the upper layer did not transmit the seismic waves as quickly as the lower layer, and therefore they're probably different materials. So that boundary was basically named in honor of our Croatian seismologist. But no one ever liked to pronounce his last name. So really within 2 or 3 years of it kind of going into the geologic literature, it was shortened to the Moho, all right? So you know you achieved it in science if they've actually shortened your last name and attached it to a boundary. And so today we view this as this boundary between the crust, fundamental layer on the outer part of the Earth, and the mantle. And that's what you can see well exposed in Oman in many, many places. So that is spectacular. And again, it's a fossil Moho. That is, it is the boundary of crust and mantle that was there at some point in the past. So, let's travel to another location in northern Oman, the Themurray anticline. And this is a mountain that I had wanted to climb before I ever got to Oman and eventually climbed it. But you can do many of these things in Google Earth before you ever get there. And this is an oblique view looking at the Themurray anticline. And the anticline is a large arch, as you'll see in a moment here. In this image, it looks a little bit like a gray slug that is sort of emerging from the Oman desert there. But I also want to draw your attention to the either side. You'll see the ophiolite exposed, those rugged brown hills. So we are going to pop into a location at the very top of this structure and take a picture. So that's where we're going to go next. And that is the image from the top of this large fold. So I'm looking off in the other direction here, but can you see this great arch of limestone in the distance? This is an extraordinarily deep canyon that's been cut there. And then, through the power of annotating our imagery, I think you get a sense that the ophiolite terrain is sort of on either side here. So let's put that into sort of a three-dimensional perspective. And to do that, we draw cross sections. And that's sort of one of the things that geologists do to see that third dimension. And we can do it sometimes by standing on a mountain and taking a photograph, all right? There's a joke in geology that a Swiss hammer, all right, in Switzerland the Alps are well exposed, but the idea of a Swiss hammer, it's a pair of binoculars, all right? So the Swiss don't have to hammer on rocks because they have such fabulous exposure. Anyway, you can use Swiss hammers in Oman because they have such fabulous exposures. The purple and the gray and the green here are limestones. Shallow water limestones. And then the brown is ophiolite. And if you were to reconstruct things, that is kind of put the landscape back together, you would end up with a situation where that ophiolite would have at some point in time been on top of the shallow carbonate rocks. And I'm pausing because I want that to sink in for a moment here, all right? And if we step back, this is actually the structure of the north part of Oman, where the ophiolite, in this instance is purple, it actually was faulted up and on to the Arabian continent. And in doing that, it actually came over a whole suite of sedimentary rocks that would have been deposited in what we call a shallow marine setting. Warm tropical seas, maybe with only a few meters of water depth, critters that were living, very productive and very happy. And in Jebel Akhtar, those limestones and carbonate rocks were exposed as a window through the ophiolite. So in essence, the ophiolite has been eroded away here, and we're able to look down at these older rocks, but the ophiolite once was on top of those. So to get the ophiolite where it is, there is a extraordinarily large and significant fault. And as a structural geologist, that's really what I study. So one more sort of animation here. This is kind of our view of what the Oman region would have looked like 90 million years ago. So Arabia would have had shallow water carbonate rocks being deposited there. See the little dot with the limestone, or LS. And the ophiolite would have been forming in the mantle all the way to the ocean floor, well out into what we call the Tethys Ocean. It's an ocean that's really no longer there. It's been removed as we have subducted ocean crust. But here's the critical thing about Oman, and I think the cool thing, is that we take these limestones, which not particularly dense rocks, ophiolite, which is actually quite a dense rock, loaded with iron, manganese, magnesium, and we have to put these rocks in contact with one another. They have been juxtaposed by a series of geologic processes, and that juxtaposition probably translated the ophiolite 300 kilometers from where it formed up and onto the continental margin of Arabia. And that is a fairly unique process. It doesn't happen everywhere. Most of the time, the ocean crust is subducted and it doesn't end up on top of the continents. So there was probably a special set of circumstances that were occurring in Oman during this time interval about 90 million years ago to get this abduction of the ophiolite and leave it where it is today. And that's why I go there. I want to look at that fault and understand what's happening at the base of the ophiolite. In fact, that sort of captures the ophiolite problem. How and why does this dense material from the crust and mantle end up over buoyant, air quotes, buoyant continental material? And Oman is the place to go answer that question. So I've taken this image from a guidebook by Gerda Hoffman and others, and it is sort of a bird's eye view of what Oman's paleogeography might have looked like prior to all of these elements that once were in the ocean ending up sort of in Arabia here. So when you explore Oman, you're going to see submarine volcanoes and reef complexes and things like that that effectively were all caught up in the sort of tectonic cannon and squashed onto the edge of Arabia. So we have studied the ophiolite and the boundary of the ophiolite in a variety of settings. As I said, I am a geologist who's excited about trying to understand the processes that are at work in fault zones. So on the left is a schematic of the bottom to the top. So the oldest rocks in Oman all the way to the youngest rocks in Oman. And they all have a fabulous story. In fact, I have a student now who's working on some of the very oldest ones, the Precambrian, Pre-Permian basement rocks at the bottom. But our studies of the ophiolite have really been focused on a layer, a boundary at the bottom of the ophiolite known as the metamorphic sole. So here's the ophiolite. It came from a distance, and it was put up and on top of these shallow limestones and older rocks there. And in that metamorphic sole, we end up with a sequence of rocks that were really exceptionally deformed in this fault zone. And when this sample comes around, I hope you'll look closely and may actually see the little chevrons and kinks. This was the sediment that was sort of caught up in front of the ophiolite as that fault ground its way sort of onto the Arabian margin there. And some of this stuff is really spectacular. So here's a photograph of Sisi and Musa pointing out the fact that they are in a shear zone. This is the major tectonic boundary. So to the northeast is the ophiolite, to the southwest are the continental rocks. And pieces of the ophiolite have actually been ripped apart, and they now look like blocks that are floating in this very thick fault zone. All right, so that's the stuff that we're really interested in understanding how and why that works. And we've been doing this in collaboration with some of our colleagues at Sultan Qaboos University. This has been actually very fruitful and very international. It's really exciting to sort of be on the ground there and go in the field with Omanis, as well as many of their professors. They've got very nice facilities there. So here we can see Musa and Cici at work in the lab. And so that's been a fruitful collaboration that we hope will continue as we keep heading back to Oman. All right, I have one or two more stories and I'll sort of open it up for questions here. This is the village of Kantab, which is sort of a suburb in Muscat. And if I had my way, I would retire there. You could swim, fish, and sail in the morning. You could ride your mountain bike, and you could look at rocks pretty much all day long. That is the ophiolite in the background. So Muscat has a little part of the ophiolite. What's exciting about it is really the palace and the National Museum are on ophiolite, and that is one of the distinctive features. So one of my favorite sort of capitals anywhere. But what's exciting about Kantab and this part of Muscat is there's so much geology to be seen in a very small place. And just look at the colors, all right? And what you'll notice is that there are 3 different colors on here. These are different geologic materials. And what's exciting about right here in Kantab, it's on what I call a geologic triple point. And hopefully you can see the fact that the green and the yellow and the blue all meet at one point. And that is the triple point. And that has sort of significance and meaning. And we're going to, in a minute, look at a cross-section view. But let's first take a look at the boundary. I'm going to go back one. The boundary between the yellow and the green is ophiolite underneath it, and then the sedimentary rocks above it. And it's fabulously exposed on the road into Kantab. Here you can see our little saloon car. Very first time I was in Oman, I had a saloon car, as it's called. I will not have one again. I have learned that you want to have a bigger, beefier vehicle if you're going to do this stuff. But the ophiolite is actually the older rock here. And after it was emplaced on Arabia, it was eroded away, and then you had younger layers that were deposited on top of it. So there's a long history even after the ophiolite was emplaced in Oman. And in the third dimension, we end up with things being quite complicated, with both of those rocks being in fault contact with the sort of carbonate strata, which are shown there in blue. And this is part of the reason I go there, that we can study these fault zones, and it's really a wonderful laboratory for geologists. And I want to wrap things up by talking about sort of a few minerals that are important in the ophiolite. And one of these is a mineral known as serpentine. And serpentine is a curious, soft mineral. And this sample, which I hope you'll have a look at, this is a fault surface, and it's actually coated with this almost glistening serpentine. It probably was almost a gel when the fault was slipping, but you can run your fingers across this and get a sense for kind of the kinematics that would have happened as one layer moved past another. And serpentine is now a very interesting mineral. In part, people think serpentine could be a very important mineral in the origin of life. And people are thinking we're going to start discovering serpentine on Mars. And Oman is a spectacular place in the ophiolite to actually go better understand that. I study it based on the fact that it's in these fault zones, but again, it's got a variety of interests. The other thing I will tell you is if you look at the peridotite in the ophiolite, anywhere, you will notice it is completely chock full of these white veins. And this is a carbonate mineral, typically magnesium and carbon and oxygen bonded together. And you can see this sort of network of fractures that are here. And it's almost at all scales, all right, that you see these carbonate veins. And what's important about this, as this ophiolite sits on the surface in Oman, it weathers, it reacts with the Earth's atmosphere. And effectively, the ophiolite in its natural state is sequestering carbon. That is, as it weathers, you are making minerals that are taking carbon dioxide out of the atmosphere to form these fracture networks. And over the last 5 to 10 years, people have thought, wait a minute, if we could actually force this process to work quickly, or if we could inject CO2 into the ophiolite, could we actually sequester carbon at a significant level that way? So there's a project called the Oman Drilling Program, which is entirely intended to answer scientific questions on one side, but then also, would there be any spin-offs that may actually have some impact on thinking about how we're going to address climate change going forward? So that is actually pretty cool. One rock to sort of speak to that, what we've discovered is that in many of the fault zones there are peridotites that have been completely turned into carbonate. In fact, they're no longer dark green and brooding. They're now sort of red and rosy. And this is a rock known as a lisphenite, and they actually occur in these fault zones. But this rock has sucked up a lot of carbon, potentially from the atmosphere, as these things form. So, perhaps the ophiolite will be important as we move further into this century. Okay, I want to wrap it all up now. I'm excited about heading back to Oman in January. We have about 24 students this time who signed up for the trip. So we have to get a bigger bus. That was our bus last time. So a bunch of gringos driving around Oman in a yellow school bus. And as I said, it's an amazing country. And I hope I've left you with a little bit of a sense that the geology there is extraordinary. And you know, if you've not thought about that, that would be yet another reason to actually be in Oman and visit it. So with that, I'm happy to answer questions. Thank you.